So, let us start our basic class on nuclear astrophysics. Okay, now here we will be discussing a lot of various techniques, and the things will be very similar to what is being done in our kitchen. In our kitchen, we take various ingredients and cook them and prepare food. And what is happening outside in the universe is that stars are basically our very big ovens where various elements are being cooked, and the byproduct is yet another elements. So basically, as you all know, most of the universe consists of hydrogen, and so what the various stars they do is that they cook hydrogen, and from there they produce other heavier elements. Okay, now so as I was saying, you see, most observed stars, including our sun, they live on the so-called thermonuclear fusion. Why thermonuclear? I will talk about just a minute. Now, what happens in such nuclear reactions? Basically, why thermonuclear? It's because these nuclears, they are induced by thermal motion. So, in such nuclear reactions, which are basically induced by thermal motion, several lighter nuclei, they fuse to form heavier ones. Now, before this process, the involved nuclei J, say they have a total mass. If it is summation mj, then you have to remember that this total mass, it must be different from that of the product mass, and the difference is what we see as the nuclear energy. Okay, so let the product mass be my, and the difference is basically known as mass defect. You know this in your nuclear physics class, right? So mass defect is basically the difference. Okay, now it is this mass difference which gets converted into energy. Okay, and using which formula? The famous Einstein's formula, right? E is equal to mc square, or in our case this mass difference, delta m c square. Okay, and you see this energy is available now, not completely but at least partly it is available for the star's energy balance. Now let us consider an example of this. Now, in a series of reactions that we will talk about later on, known as hydrogen burning, what happens is that 4 hydrogen nuclei, they have a total mass of, you will see, 4 into 1.0079 mu. I am writing in terms of atomic mass units. Now this is transformed into 1 helium nuclei. Now this is not a straightforward reaction. There are various steps in it. Because you see, let us consider a real life example. How many accidents do you see where 4 vehicles are involved? You don't see. Have you ever heard anything about it in your lifetime of 25 years or something? Very rarely. But how many 2 accidents where 2 vehicles are involved have you heard? Plenty. Every day open the news channel and you will hear about it. So this means that such possibilities are very rare. Similarly, in our case also, reactions involving four hydrogen acting together, fusing, this is very rare. So what happens is that this is not a straightforward reaction. There are many subtleties involved in it. So what basically happens is that these four hydrogen nuclei, they fuse in various steps of two-body reactions, and these are collectively known as hydrogen burning. Okay, hydrogen burning. We will talk about the details when I talk about the hydrogen burning after discussing basic ideas about reaction cross sections. Okay, now, so as I was saying, so they are transformed into one helium nuclei and it has a mass of, 4.0026 atomic mass units. Okay, now you see these atomic masses are given for the neutral atoms, that is for nucleus plus all electrons. However, you see, since the electron mass is roughly, mass of an electron is roughly 1 by 1823 of mu, right? So we can assume that all masses of nuclei are the same as the atomic masses, right? So because of this we can consider that. Now, so what's the difference between the two? The difference is of the order of, difference is, you see, it is of the order of 2 into 10 to the 2.9 into 10 to the power minus 2 atomic mass units. And you see, this difference is produced per helium nuclei, which have, okay, and this is produced as a result of the disappearance of the 4 protons. And what is this fraction? Now this, you see, this difference, if you do the division to the original mass of 4 hydrogen atoms, then you will see that difference comes out to be around 0.7%. So this means that roughly 0.7% of the original masses is converted, and this corresponds to about 27 MeV. If I use this, delta E is equal to mc square formula. Okay, so basically this much energy is produced just as a result of formation of one helium nucleus. Now you must be wondering how much is this energy in terms of temperature and so on. So let me give you a rough estimate. You see, in nuclear physics you must remember that we normally take the scales as electron volts, right? Now you must remember this fact that 1 keV, it is approximately equal to 1.16 into 10 to the power 7 Kelvin. I am writing in terms of temperature. And how much is one atomic mass unit? This is, you also know, it is approximately 931.49 MeV, and this corresponds to approximately 1, yes, here, atomic mass unit. Okay, this is just basic idea for you to remember. Okay, now next, so what do we have? We have this amount of energy, 27 MeV. Now what about the sun's luminosity? So sun's luminosity, you see, if we consider the sun's luminosity, then this corresponds to mass loss rate. The energy is being continuously emitted by the sun, right, which is given by this luminosity, and this corresponds to mass loss rate of L luminosity by C square, and this is 4.26 into 10 to the power 12 gram per second. And now this is a very large number. very large. You see? Okay. Now, if a total of, let us consider this, suppose if a total of 1 solar mass of hydrogen were converted into helium 4, then what? Then you see the disappearance of 0.7% of mass will be 1.4 into 10 to the power 31 gram, right? And this, you will see, this could balance, this is amazing, this could balance the sun's present mass loss by radiation for about 10 to the power 11 years. Okay, you can do this yourself and check. How can you do that? So, how do you get this number of 10 to the power 11? You just divide this 1.4 into 10 to the power 31 gram by the mass loss rate. Okay, and then you will get this number. So how much is this? 10 to the power 11 years. And you see, using this nuclear reaction, we can explain how the sun has been burning for so long. We can explain the age of the sun. Okay. Now, you see, it is important to remember that this deficiency of mass is just another aspect of the fact that the involved nuclei have different binding energies. Now, this is the energy required to separate the nucleons, basically neutrons and protons, against their mutual attraction by the strong short-range nuclear forces. Or else, you see, the energy gained, or you can also say that binding energy is basically the energy gained if they are brought together from infinity. Okay, now let me consider another part. So let us have a short discussion on binding energy. So again, let us consider a nucleus of mass m nuclei, atomic number A, okay, Z protons, okay, and each having mass mp. And how many neutrons? Of course, A minus Z neutrons, and they have mass mu. Now, you see, so the binding energy is EB equal to A minus Z Mn plus ZMP minus M nuclear into C square. So as I was just saying, when comparing different nuclei, for different nuclei, it is better to consider an average binding energy per nucleon, or basically EB per A. But this is also known by another term, which is binding fraction. Basically, now I am talking about nuclear physics. Come on, the topic is nuclear astrophysics. So you just cannot avoid nuclear physics, right? And this is also very important. Well, you see, with the exception of hydrogen, let me first plot this binding energy, binding fraction. So this is this should be straight somewhat. Okay. Now this peak, it occurs around 50. Okay. And so on, 100, 150, and so on and so forth. And this is your binding fraction, and again here it is around 8 MeV. So this is 4 MeV. Fine. Now, so you can explain this thing, right? We have been seeing this thing for so long, but just let me spend some more time on it. Now you see, with the exception of hydrogen over here, typical values are around how much? 8 MeV, with relatively small differences for nuclei of different mass. Now this shows that the short-range nuclear forces due to a nucleon mainly affect the nucleons in its immediate neighborhood only, such as with increasing mass number. What happens is that a saturation occurs here rather than an increasing of F. So instead of keeping on increasing, a saturation occurs. Now let us discuss this. Why? You see, with increasing mass number, this part over here, Fa, it rises steeply from hydrogen and then flattens out after reaching a maximum of around here 8.5 MeV, and this is around 56 iron. Okay. Now why does this increase? This part, you see, this increase is for mass less than 56. Now this is basically a surface effect. How? You see, particles at the surface of the nucleus, they experience less attraction by nuclear forces than those in the interior. Remember the Bethe-Weizsäcker mass formula? I am just explaining the surface term of that. Okay, now the interior nucleons, they are completely surrounded by the other particles, right? And the outer ones are only surrounded by one part. Another part we do not have. So they are experiencing less attraction. And what happens in a densely packed nucleus, the surface area increases with radius slower than the volume or mass number, such that the fraction of the surface drops rapidly. Now with increasing mass number, the number of protons, another thing happens. Now let me explain the Coulomb term. So with increase of mass number, the number of protons also increases. Now the addition of the neutrons, they also increase, and that would require higher energy states, because you see, Pauli's exclusion principle excludes more than two identical neutrons, and the nuclei would be unstable. So what happens is that the positively charged protons, they experience a repulsive force, and which is much more far reaching. The range is much higher as well. Coulomb force has range of infinity, and therefore it does not show a saturation of nuclear forces. Now this increased repulsion by the Coulomb force brings this curve down. So this is surface effect, and here there is Coulomb effect because of that. Now around the maximum we have the most tightly bound nuclei, or in other words 56 iron, which has the smallest mass per nucleon. So that any nuclear reaction bringing the nucleus, any nuclear reaction from this part bringing the nucleus closer to this maximum will be exothermic. That means it will release energy, and this is what we want in stars. We want energy to be released, not to be absorbed, and that's why we are studying this binding fraction curve. So what are the two types of releasing energy? Those are to go from either this side or from this side, that is by fusion of light nuclei or by fission of heavy nuclei. Okay, Now clearly both reach an end when we try to extend them over the maximum of F, which is therefore a natural finishing point. So this one, our aim is going from this side, and this is where we have the maximum. Okay, so if a star initially consists of pure hydrogen, it could gain a maximum of 8.5 MeV, you see, per nucleon by fusion to 56 iron. But 6.7 MeV of these are already used up when 4 helium is built up in the first step. Remember. Now, in order to obtain a fusion of charged particles, what do we need? The first thing we need is we have to bring them together, right? So, fusion of charged particles. The first thing is we have to brought together, brought close together, so that they can experience the strong nuclear force. Of course, this doesn't mean the Coulomb force will vanish. Coulomb force will always be there, but what we want, the nuclear force to dominate the Coulomb force, and for this they must be brought very close to each other. Now, the counteraction of this nuclear and Coulomb forces, it leads to a sharp potential jump at the interaction radius. Let me show you. So, yeah. So, this is the energy, and here no, not this one, just a second. দাঁড়া আরেকবার। Yes, এটা কিন্তু টাচ হয়নি, এটা কিন্তু এই রকম করে বেরিয়ে যাচ্ছে। ওকে, it will not touch, remember. Okay, so this is the Coulomb barrier that I will talk to. Approximately equal to Z1 Z2 MeV. Okay, this is R0. You will see that I will consider a nuclear, a proton very soon having energy E1 entering, and so it will reach up to R1 and then classically bounce off also. And this is your depth of the potential, again of the order of 30 MeV. Okay, so now I was saying the first thing is that we have to bring the particles close together so that the nuclear force, attractive nuclear force, dominate over the repulsive Coulomb force, and the counteraction of these two forces lead to a sharp potential jump at the interaction radius. So how much is this interaction radius? Well, we know it is approximately a to the power 1/3 into 1.44 into 10 to the power minus 15 meter. So basically the nuclear radius. Okay. Now for distances less than R0, the nuclear attraction dominates and provides a potential drop of roughly 30 MeV. While what happens outside is that repulsive Coulomb forces are present particles with charge Z1 and Z2, and as a result we have the Coulomb force being equal to Z1 Z2 E square by R. I am just writing, forgetting about 1.4 pi epsilon 0 term. I am using the CGS units. I can use that, right? Fine. So this is the repulsive Coulomb force for particles with charges Z1 to Z2. I am just taking an order roughly. Now what about the height of this Coulomb barrier? So this is this height is the Coulomb barrier. And what is its height? So Coulomb barrier, the height is basically E Coulomb at this R0, and you see it is approximately Z1 into Z2 MeV. Fine. Now let us consider this. Let us consider the reference frame of the nucleus. Now, so in the stationary reference frame of the nucleus, a particle at infinity has kinetic energy E1 here. Now, how close it can come? Now, it can come classically only up to a distance R1 here, given by, so what is E1 at that time? So you can say E1 is basically equal to E Coulomb at R1, right? Using this above relation over here. Now, the kinetic energy available to particles in the stellar interior is in that of their thermal motion. Okay, so kinetic energy available to particles in stellar interior is thermal motion, and hence the reactions triggered by this motion. So the reactions triggered by this, so nuclear reactions triggered by this thermal motion, they are known as thermonuclear reactions. Okay. Reaction. Now, in normal stars, we observe a slow energy release rather than a nuclear explosion. And so, we must expect the average kinetic energy of the thermal motion to be considerably smaller than the E Coulomb, right? Here. This Coulomb barrier, our thermal motion must be lower than this, otherwise we will see an explosion, right? Now you see, for values of, say, stellar core temperatures of the order of 10 to the power 7 Kelvin, you see, what is the value of kBT? kBT is roughly of the order of 10 to the power 3 eV. Okay, so you see that your E thermal is much lower. And what is the Coulomb barrier? Coulomb barrier, remember here, this is the Coulomb barrier, Z1, Z2 MeV. So I am talking about how much? 1 MeV, Coulomb barrier. So compared to this, this is 1 keV. So you see this thermal energy, so this is the thermal energy divided by E Coulomb is of the order of 1 by 1000. So you see our thermal energy is of the order of 1000 times lower than the Coulomb barrier. and this is in fact so low that with classical effects only we can scarcely expect any reaction at all. Now let us consider the Maxwell-Boltzmann distribution. Okay, because stars in the sun, they roughly follow the Maxwell-Boltzmann distribution, and you must remember that in the Maxwell-Boltzmann distribution the high energetic particles are in the tail, right? So in the high energy tail, in this high energy tail of Maxwell-Boltzmann distribution, this exponential factor because of this 1 by 1000, this drops to, remember we have this term in the Maxwell-Boltzmann distribution, e to the power minus e by kt, right? So I am just considering this Coulomb by this term, Coulomb by thermal energy. So the exponential factor here becomes e to the power minus 1000, and this comes out to be of the order of 10 to the power minus 430 something, say 434. So what does this mean? What does this mean? This means that there is hardly any chance for nuclear reaction to happen. And how many number of protons are there? How many number of nucleons? Say nucleons in the sun, solar mass, and if you estimate this, you will find that this number is around 10 to the power 57 nucleons. So you see, if you do this maths, 10 to the power 57 into 10 to the power minus 434, still this is much less than 1, right? So what does this mean? This means that there is hardly any way any thermonuclear reaction can happen in the sun. Now in fact, if we consider the entire universe, entire universe, then in this entire universe there are approximately 10 to the power 80 nucleons. And even so, you see, even with 10 to the power 80 nucleons, we cannot explain classically the thermonuclear reactions. So what's the way out? Of course, reactions are happening. Otherwise, how can you be doing this online class? How can you be seeing your smartphone? None of this will exist. They exist because of elements other than hydrogen, which are produced in the star's core as a result of the thermonuclear reaction. So this means there is a catch. And so what's the catch? You know the answer. Well, so the only possibility for thermonuclear reaction in stars, it comes from quantum mechanical effect. And this was found by George Gamow. Okay, and you see there is a small, so what's the effect? So the effect is that there is a small but finite probability of penetration or tunneling through the, okay, so yes, where was I? So yeah, so there is a small penetration or tunneling through the Coulomb barrier, and that probability we will estimate it using quantum mechanics. So this finite probability of penetration through the Coulomb barrier is there, and this is the quantum mechanical tunneling probability. You see, and this is present even for particles with energy lower than your Coulomb barrier, right? And what's this? I am not doing the entire maths here, I am just writing down. So this tunneling probability is given by, you see, P. There are many ways of writing it. Now, of course, I can write it in this way as well. E to the power minus 2 pi eta, where this eta is equal to m by 2 to the power half z1 Z2 E square by H cross E to the power half. Right, so you have already seen this thing before during the alpha decay. Right, now you see this can also be written another way of different coordinates, but in a much, what will I say, a better way to understand. We can write it as this. So this P0 is basically penetration probability. So this is approximately equal to exponential minus EG by E, এইভাবে লেখা হয় অনেক সময়, ঠিক আছে? ওই একই জিনিস ঘুরিয়ে ফিরিয়ে লিখছি, কিন্তু দিস ইজ আ বেটার ওয়ে টু আন্ডারস্ট্যান্ড। এটা অনেক শর্টে আর কি হয় হিয়ার। And what is this EG? This EG is basically known as gamma energy after George Gamow. I'll come to this later on. এটা নিয়ে একটু বলবো, আমি ডিসকাস করব। এনিওয়ে, গ্যামো এনার্জির এক্সপ্রেশনটা হচ্ছে দেখো, twice mr c square into alpha pi alpha এই দুটো যে নিউক্লিয়ন into c square. This is it. Now before that, let me do some explanation. কি হচ্ছে? Okay, so you see there are two ways of writing this. Now this is an approximate way, and what about this way? What is this? So let me try to explain this term. You see, this factor P0, it depends only on the properties of the two colliding nuclei, and we have got an exponent here. So there are three things. One is this P0, another is energy dependence, and another is this exponential term. Not 2 pi, but rather this eta. Okay, now this exponent is obtained as the only energy dependent in an approximate evaluation of the integral, okay, over this E Coulomb minus E by half, which is extended from this here, and this is extended, you see, let me show you the graph, where was it, yeah, and this is extended from this R0 to a distance of closest approach. Right, now let us do some number estimations. You see, for Z1 Z2 equal to 1 and T is equal to 10 to the power 7 Kelvin, P0 is of the order of 10 to the power minus 20 for particles of average kinetic energy E, right? And this steeply increases with energy and decreases with, so this increases with energy and decreases with Z1 Z2, the product. Therefore, for temperatures even for as low as 10 to the power 7 Kelvin, only the lightest nuclei. Why lightest? Because they have the smallest value of Z1 Z2. They have a chance to react. For reactions of heavier particles which have large Z1 and Z2, the energy, or basically the temperature, needs to be very large so as to provide comparable penetration probability. And as a result of this, what we have is a well separated phase. We have a well separated phases basically of different burning during the star's evolution. Over here, so this is the expression as I am saying. So I just explained this term, this is another term. We will talk about this more in details as well. Now, so if I ask you, does a higher gamma energy increase or decrease the probability of penetration? What will you say? Higher value of this. You see, a higher gamma energy, it basically reduces the probability that the barrier will be penetrated. And in a way, the gamma energy measures the strength of the Coulomb repulsion, which determines the height of the Coulomb barrier. Now, let us do some more calculations. So, I would like you to estimate this. So, calculate, let us, examples, let us calculate this gamma energy, okay, for number 1, collision of 2 protons. Let us try. Yes, so first we will consider this and later on we will do the second example, which is basically there we will consider again the collision, but not of protons, but collision of 3 helium nuclei. Okay, and let's see the difference, what we observe. So let me show you. So the first part, which is the collision of 2 protons. Now let me write down the gamma energy. So Eg is equal to 2 mr c square pi alpha Za Zb, okay, whole square. What is mr? It is basically the reduced mass, Ma plus Mb. Okay, so let us first estimate the reduced mass for this 2 protons. Now it comes out to be how much? Mp square by twice of Mp, so or basically half of Mp, and this is approximately 8.36 into 10 to the power minus 28 kg. So with this it is possible to estimate this value, and if you do the estimate you will see that it comes out to be 7.9 into 10 to the power minus 14 joule. Again, we know that how much is joule? 1 eV is 1.602 into 10 to the power minus 19 joules. So if we keep this in mind, then we can write this as, you see, I would like you to check this number, and finally Eg comes out to be 494 approximately keV for 2 protons. What about the 2 helium nuclei? So the next example, right, for 2 helium nuclei, again let me first calculate the reduced mass. So it is basically M3 by বলো কোনটা? alpha হচ্ছে 1 by 137 approximately, fine structure constant 1 by 137, ঠিক আছে? আচ্ছা, now this again or basically 3 Mp by 2. We are talking about 3 helium. So this comes out to be around 2.51 into 10 to the power minus 27 kg. Right. After that, let us estimate this. And again, if we do the estimation, এটা বেরোবে দেখো 3.796 into 10 to the power minus 12 joule. আমি পুরো ক্যালকুলেট করে তোমাদের নাম্বারস দেখাচ্ছি। তারপরে জুলটাকে যদি আমি ইভিতে কনভার্ট করি, then you will see that the value comes out to be around 23.7 MeV. ওকে, এটা একবার তোমরা চেক করো। হ্যাঁ, কি বলছো?
স্যার ZA আর ZB
হ্যাঁ
আই আলফা জেড এ জেড বি তার হোল স্কয়ার যেটা আছে
হ্যাঁ
ওইখানে জেড এ আর জেড বি দুটোই 1 1
হ্যাঁ দুটোই 1 হবে আগের এক্সাম্পলে। ওটাতে দুটো প্রোটন আছে না?
হ্যাঁ স্যার ঠিক আছে
বলো। হ্যালো, ক্যালকুলেশন
ঠিক আছে
ঠিক আছে? আচ্ছা ঠিক আছে, গুড। সো what do we observe is that the addition of one additional charge on each of this 3 helium compared to the proton, there is one additional extra charge. Okay, and this increases the gamma energy by a factor of 16 or so compared to the proton-proton collisions. Have you checked this second calculation? This one, if it is coming or not, I would like you to check this. Okay, so we did these very basic calculations on gamma energy also, right? What about next? Now next, let me do yet another calculation, another example. Now this time I am telling you that in the sun's core, suppose sun's core, I am telling you that the temperature is approximately 15.6 into 10 to the power 6 Kelvin. Okay. Now, so you see, what does this mean? This means that kBTC, thermal energy, it is approximately 1.3 keV. Okay. So I would like you to estimate the penetration probabilities for the 2 proton and the 2-3 helium nucleus collision case. What will be the penetration probability? Let us calculate this time. You see, this is not very hard. Let me help you. Now we know this penetration. We don't have to consider the entire term. Let us use this short expression, right? E to the power minus Eg by E to the power half, right? Or this is approximately equal to exponential minus Eg by kB Tc to the power half. So what about PP collisions? If we do this, then we have basically exponential minus 493 or 493.6 actually divided by 1.3 kV, right, to the power half, and you see this comes out to be 3 into 10 to the power minus 9. What about the 3 helium collision? This one again, if you do this similarly, then you will see that this comes out to be around minus 59. Now this is a very small number, right? So what you can say, what is the range? So the range is roughly from 10 to the power minus 10 to 10 to the power minus 60. So what do we see? So what we see is that even with quantum tunneling, the probability that any particular pair of nuclei will react is extremely small. Okay.
স্যার 10 টু দি পাওয়ার মাইনাস 59 টা স্যার অনেক কম, মানে প্ল্যাঙ্কের লেন্থের চেয়েও কম।
আমি এটা পেনিট্রেশন প্রবাবিলিটি বলেছি, এটা কোনো লেন্থ বলিনি বাবা। আই এম কনসিডারিং দ্য প্রবাবিলিটি।
মানে তো স্যার ওই 1/e টাইমস যতটা যাবে সেটাই তো তার ডেপথ।
আমি এটা পেনিট্রেশন প্রবাবিলিটি ক্যালকুলেট করছি, এটা কোনো লেন্থ নয়। আই এম জাস্ট, দিস ইজ এ প্রবাবিলিটি অফ ওকে দিস নাম্বার দিস থিং অ্যাকচুয়ালি এটা ক্রস সেকশনে কিভাবে এফেক্ট করবে এই জিনিসটা এখনো আমি আসিনি, আমরা আসবো, এখনো ওই জায়গায় পৌঁছইনি। ওকে উই উইল কাম ইভেনচুয়ালি। ওকে সো we have more or less completed the first part of today's lecture, and that was consideration of the basic interactions, so basic considerations of classical trajectories, right? Then we observe the difficulties, and next the difficulties were solved by using the quantum mechanical tunneling, and after that we calculated the values for gamma energy for two very important cases, right? So this is what we have done till now. Now before I proceed, let me again go back to the basic considerations. What we did previously was we talked about nuclear reaction in general, binding energy, we talked about it, and then we talked about the binding energy, binding fraction. No, not this one. So basically we talked about this plot of binding fraction as a function of mass, right? Now the next important topic is nuclear cross section. This is very important. So this is what we will discuss now, and after that again we will compact this idea of gamma energy with nuclear reaction, and then finally we will talk about the thermonuclear reaction rate estimation. This is the way we are proceeding. ঠিক আছে? Okay. Now let me talk about nuclear cross sections. Okay. Now let us consider a reaction of the nucleus X with a particle A. So we can write like this. So nucleus X reacts with particle A, and as a result it gives nucleus Y and another particle B. Now often we use this notation to indicate this nuclear reaction. Now let us try to explain the reaction probability, how it depends on the nuclear details. Okay. Now you see, after penetration of the Coulomb barrier, what happens is that an excited compound nucleus C star, compound nucleus C star, it is formed. Now it contains both original particles. What about the level of excitation? Well, the level of excitation in this compound nucleus is dependent on the kinetic energy and also the binding energy brought along by the newly added particle. Now this is just basic ideas about compound nucleus theory, and this will be important in our astrophysical calculations. That's why I am discussing this. Now you also remember that this compound nucleus, light jaliye na, this compound nucleus may decay after a short time, which will still be long enough for the added nucleons to forget owing to interactions within the compound nucleus, that is their history, a process for which only of the order of 10 to the power minus 21 being necessary. Now the decay then depends only on the energy of this. So decay depends on energy. Now there are several possible channels, each having different probability of decay, right? So we can have this channel X plus A, or we can have Y1 plus B1, another channel. So various channels or output possibilities. So you see, the first possibility is basically sort of reverting back to the original. That means reproduction of the original particles. While this one, the last one, we can also have something like this. Say C plus gamma. What is this? Again the same nucleus but in a de-excited state. Same as the compound nucleus. And the de-excitation is possible by the emission of, by a gamma ray emission. And what about the others? These are basically particle emissions, where neutron, proton, alpha particle can be emitted, right? Now, so you see the possibility that a given energy level of C star can decay via a certain channel requires consideration of various conservation laws. Okay. Now let me show you a schematic sketch of the levels of the compound nucleus. So here I am showing you a schematic sketch of the various energy levels in the compound nucleus C star. Okay. So compound nucleus C star. Now the zero of this energy here is taken as corresponding to the zero velocity of x and a at infinity. So right. Now for initial energy E1, say this one, the reaction will be non-resonant. While for E2, you see the particles and XA find a resonance in the compound nucleus. Here. And what about this E min? What is this? This is basically the minimum excitation energy above the ground level for particle emission. Okay. So, right. So what we are seeing here is basically the different levels of the compound nucleus, C star. Right. And you see these levels can be of various types. Say for example, what is this E mean? As I just explained, this is basically the minimum energy required to remove a nucleon from the ground state to infinity with a zero velocity. That is to the level E is equal to 0 here. Now, this corresponds to the atom ionization energy as well. Now, what about levels above E min? So, this is atom ionization, right, energy. Okay. Now, there are other levels as well. Now, they are obviously below this E min, they can decay only by electromagnetic transitions with the emission of gamma rays, which are relatively improbable, and hence their lifetime is large. So these are basically stationary levels of small energy with gamma, and we can write this gamma as h cross by tau, which also you can get from the Heisenberg's uncertainty principle. So these levels basically correspond to the discrete bound atomic states. Now this compound nucleus, you see, will not immediately expel a particle if its energy is somewhat above this E min. Since the sharp potential, you see, it rises, this potential rise will hold it back, at least for some time. Eventually, it can leave the potential well by the tunneling effect. And this is how, you must remember, we explained the alpha particle decay. Right. Now, and this tunneling effect is the same as by requiring the calculation of the tunneling probability. So, there can be quasi-stationary levels above E min that have an appreciable shorter lifetime, and as a result they are considerably larger. So, shorter lifetime means larger width over here compared to these levels. And since they can also decay via the much more probable particle emission, right, Now this probability will clearly increase strongly with the increasing energy here, and this results in corresponding decrease of tau and increase of width. Now above a certain energy, say Emax, this width will become larger than the distance between the neighboring levels, and their complete overlap will yield a continuum of states like this here, instead of separate discrete levels. So you see, next one. Now, so the possibility, or you can say the possible existence of these quasi-stationary levels above E mean, they requires particular attention, and this will be the ones which will play a role in astrophysics. Now let us consider an attempt to produce the compound nucleus C star by particles x plus a with gradually increasing energy of their relative motion at large distances. Okay, so what will we observe? What we will observe is this, you see. So if this is energy and this is the cross section and these are the energy levels, so what we will observe is this. And what are these bumps? Sorry, this is how. What are these bumps? They will correspond to these energy levels. You see this one, E1, E2, and so on. Okay. So you see this reaction probability will simply increase with the penetration probability here. Now if E is in a region either without quasi-stationary level or between these two levels, this is what will happen. However, if E coincides with one such level, the colliding particle, it finds a resonance. Here, this is the result of the resonance, and can form the compound nucleus much more easily. What happens is that at such resonance energies, E resonance, say, the probability for the reaction and also the cross section is enhanced, as you can see from this figure. And as a result, we have resonant peaks. In fact, this is not a linear plot, this is a log plot. And so, these resonance peaks are sometimes several powers of 10 above this one. So, this is not a normal plot again. Now, what about the energy dependence of this resonance? So, energy dependence of this cross section, this has a form, in fact, of the order of, you see, E minus E resonance whole square plus this width by 2 whole square. This is the form. Now at resonance, this cross section for the reaction of particles X and A, they can nearly reach its maximum value. So at a resonance, this sigma, it reaches the maximum value, which is the geometrical cross section. And from quantum mechanics, you know what is the value of this geometrical cross section? Simply pi lambda cross square, where this is the de Broglie wavelength. So this lambda dB is basically h cross by p equal to h cross by root over 2me. Now we have used the non-relativistic relation between the two of them, and remember this m is here the reduced mass. So you see the meaning of this, just a second, let me write down this energy dependence of this cross section. Let me give it a term, say chi of E. This is the energy dependence at near resonance. Okay, so okay, now this meaning of pi lambda square is clear, because according to quantum mechanics, particles moving with momentum c each other, not as precise point but smeared out over a length of de Broglie wavelength. So the dependence on sigma on energy E is roughly, you see, it is proportional to, first we observe that this is proportional to the penetration probability. Next we observe that there is an energy dependence as well. Next we observed here that it also has a dependence on pi lambda square. So if we consider all these effects, then we see that sigma of E is proportional to pi lambda square P0 at E, or penetration probability, into this Bright-Wigner resonance term. Okay, now for energy below Coulomb barrier, we can take P from previous values, right? Now also we can take P0 as we have considered previously. And also, what about the single resonance? For a case of single resonance, we have the Xi factor that we also have considered before. However, if we are far from resonance, so this is near single resonance, far from resonance, what happens is that this term goes to 1. There is no dependence, energy dependence. Now in any case, with or without this resonance, this is always proportional to this lambda square into P0. This is with or without resonance, right? And as a result, you see, we can write this sigma E as a result of this. We can write this sigma E term as equal to S into, this is basically what? 1 by E. So S into 1 by E into this penetration probability, or basically e to the power, just a second, sometimes it is written like this, e to the power minus 2 pi eta. Also we can use the Eg term as well, but this is more or less the general form. Note that here all remaining effects are contained within this S term, and this is known as astrophysical S factor. So basically this factor contains all intrinsic nuclear properties of the reaction under consideration, and it can be calculated. However, we have to rely most of the time on experiments. Now why is this so? You see, this S is not fixed, it is a slowly varying function of energy, Se, and there are several difficulties in its measurement. Now when I say measurement, I mean measurement in the lab. Sometimes it is not even possible to measure them. Why? Because of very small cross sections. And so they are rather feasible only at high energies. So the measurements is possible above say 0.1 MeV. But this is still roughly a factor of 10 larger than those energy which are relevant for astrophysical applications. So what we do sometimes, we have to extrapolate the measured Se. So we do, what do we do is that we extrapolate the measured AC downwards over a rather long range of energy. Now this can be done quite reliably for non-resonant reactions. This is okay for non-resonant reactions, in which case S is nearly constant or a slowly varying function of E. Right. The real problem arises in case of resonances in the energy range over which our extrapolation is included, and then the results become quite uncertain. Now these experiments, they are normally performed in underground laboratories. Why? Because the cross section is very small, and in our measurement, if there are other background counts from cosmic rays, from other background sources, say for example the cement, the earth and all that, so we have to reduce this, and that's why we go underground. And we also use special detectors, low background counting detectors for these measurements. And doing so, it is sometimes possible to measure the nuclear cross sections, again of at least a few nuclear reactions, as at energies as low as 10 to 30 keV. This is possible. And this is the energy relevant for nuclear processes in stellar interiors. Okay. Now, any questions? So, we have completed the second part, right? So, we have considered about the reaction cross sections, and we discussed this very important topic of astrophysical S factor. I have a little bit discussed about their measurements, how they are performed. Now, coming back to reaction cross section, nuclear reaction cross section. Now you must remember that I have already derived this nuclear reaction, how to estimate, in the composition equation section. This we have discussed previously. I am just going to write down the result here. So basically the result which we derived there, it was like this: Rix. So basically the reaction rate was written like this: Rix is equal to Nx Ni, two species, so reaction rate between species I and X, so Xi, then the cross section, right, sigma E, followed by the velocity. We did not include the Maxwell Boltzmann calculations over here, we just write it down as it is, and then we have the Ne by N term dE. So this is how we estimated. I have already discussed using diagrams, all that stuff. Now what I am going to do, I am now going to include the Maxwell Boltzmann distribution in this part, and then do the calculations also after including the effect of penetration factor. So right, so let me write it down. So now incorporating the penetration factor S factor and Maxwell Boltzmann distribution in the speed averaged reaction cross section, we will get, I am just writing down the expression, and the expression is, you see, this. Now instead of X and I am now using this term AB between the two species. So they are species A and species B, and the term is Na into Nb, and this is the you see fusion rate per unit volume. So Na into Nb, next term is 8 by pi, and this is Mr or rest mass, to the power half 1 by kBt to the power 3 by 2, right? This is coming from the, you remember this, all the terms previously discussed, so I am using this, and as a result you will get this, and multiplied. What about the S factor? Now comes the S factor. So speed averaging, here is the S factor into exponential this minus E by kBt minus Eg by E to the power half dE. This is the term. So fusion rate per unit volume. This is what we have. Now you can note certain very important things from this expression itself. What are they? The first is that this Na and Nb, this is basically gives you the number of possible reactions. Okay. Now where is this 1 by kBt 3 by 2 terms come? This comes from the, this term, this comes from the Maxwell Boltzmann distribution. Okay, this term comes from there. And we already know that this AC, Astrophysical S Factor, so it tells us about the strength of nuclear interactions. Right. Now, what about this term, Eg by E? It indicates basically the probability of tunneling through Coulomb barrier. And what about this E by kBt? Again, this is the Maxwell Boltzmann thermal energy distribution. Okay, so I have explained to you each of the terms over here. Now, why have I written this part out separately? There is a reason, because you see there is energy dependence over here. So let me discuss this part separately. So the energy dependence of reaction rate. Right, and this is given by this term, 0 to infinity AC into exponential minus, let me put this term first, Eg by E to the power half minus E by kBt. Okay, dE. Any questions? Okay, so this is what we did previously, and now just a second, maybe I have skipped this part. Okay, so this is the term, right? Now, so we can write this as separately. Again, 0 to infinity AC exponential. This time I am separating the terms, to the power minus Eg by E to the power half and into exponential minus E by kBt, and then dE. Now you see the nuclear S factor, this one, so we have three terms, 1, 2 and 3, three terms. You see this nuclear S factor, it varies only slowly with energy, we know, apart from near low energy resonances. So essentially all of the energy dependence come from the exponential terms, these two. Now this term, you see this one, it increases as kinetic energy of the nuclei increase, but this one, this decreases. So the product of the two is small at high and low energies, and they become significant only over a range of intermediate energies. And this behavior, let me show you in diagram. Okay, so you see this is the fusion probability and this is energy, and you see this is your tunneling probability. Okay, and here we have the Maxwell distribution. Okay, and the result of these two, when the two terms are multiplied, is that we will get something like this. And this is the gamma peak. Okay, now you see what I am showing you here is basically the behavior of these two terms in this plot I am showing you here. And what we observe is that as a result of this distribution, this peaks at an energy, and this is known as the gamma peak. And what is the value of this gamma peak? This energy, gamma peak. This has energy E0, gamma peak. Let me write it down. So the value of E0 is basically, this is related to Eg, as you will see, Eg into kBt by 2 whole square, and this one to the power 1 by 3. Okay, now this is interesting, and in fact I would like you to show this yourself. So this is a homework. So show that this distribution, this energy dependence of cross section, dependence of nuclear reaction cross section peaks at E0. It's just a maxima minima problem. I'd like you to do this yourself. This is not very hard, but also quite instructive. Okay. Any questions till now? Bolo. So basically we have considered the concept of gamma peak. So the energy dependence of reaction rate. Okay. From there we considered only these two terms, and from there we introduced the concept of this gamma peak. Introduced here. Okay, now next, so we have just talked about this thing. Okay, so you see we have this gamma peak, and so this is your peak energy or gamma peak energy. you see, this is important. Also, this width or width of the gamma window, right? You see, this is gamma window. So it has got two very important attributes. One is peak and another is this window width. This is also very important. How, you see, because from this figure, what we will observe, we are observing here. Okay, so let me again tell you what this figure tells us. Basically, we are basically seeing the effect of the two terms of the exponential, right, when the product is made. And what we are observing is that the energy at which the fusion rate is maximum, we get a peak. Note that this is not entirely a Gaussian peak, and this peak is known as gamma peak. And the region on the ideal side of the peak in which the fusion probability is significant, this is known as the gamma window. This is what we are observing. So what next? Next is the gamma window width. So you see, there is a range of energies, a large number of energies are possible, which if they are in this gamma window, then the reaction rate will be significant. So basically there is a certain range of energies or window. We don't have to calculate over all the energy ranges to find or to estimate where the reaction rate, to estimate the entire reaction cross section. We have to consider the reaction rate where it is maximum, and this is maximum in this part, in this gamma window. Now in order to examine the fusion rate in the vicinity of the gamma peak, the quantity we have to quantify, basically the width of this window. So let me rewrite this term as, you see, RAB, just a second. Okay, so let me rewrite this as RAB is equal to NA, NB, then the two terms, and then your integration term AC. Now this time you see what I am writing, into exponential minus FE dE. Okay, and what is Fe? This minus of Fe is equal to your this term minus Eg by E to the power half plus E by kBT. The entire concept here occurs because you see of this fact that the energy dependence is different in these two terms. Here it is in denominator, here it is in numerator, and as a result of this we are getting this peak. Okay, fine. Now to investigate the width of the window, let us do a Taylor series expansion. So of Fe, and if we do that, then you will see that if we consider the entire terms of the Taylor series expansion, then I am writing down the result. The result is like this: Fe is equal to 3 Eg by kBT to the power 1 by 3 plus half of you can also check this yourself, this expansion. This is also maybe a homework activity for you. Check this if it is so. Half of E minus E0 square into 3 by 2 to the power 1 by 3. And what about the energy dependence? Energy dependence is Eg minus 1 by 3 and kBt minus 5 by 3 plus other terms. Now you see, so we can rewrite this term as 3 times Eg by kBt to the power 1 by 3 plus E minus E0 divided by this delta by 2 to the power square, and this delta is the gamma width. So the gamma width is the delta, which is given by this value, 3 to the power half into 2 to the power 1 by 3 into Eg to the power 1 by 6 into kBt to the power 5 by 6. Now this characterizes the range of energy. So this characterizes the range of energies over which the fusion is likely to occur. Okay, so with this we can write, you see, the entire reaction cross section, the integrand for the reaction part. It can be right, so reaction rate, so this is equal to, basically again you can write Na, Nb, then this 8 by pi mr or reduced mass term into 1 by kBt to the power 3 by 2 into 0 to infinity AC into exponential minus 3 Eg by 4 kBt to the power 1 by 3, again into exponential minus E minus E0 divided by delta by 2 to the power whole square dE. Okay, so this is what we have. Now you see, this gamma width can also be written as, sometimes we also write it like this, Eg by kBt to the power 1/6 into kBt. And what about the half width? So basically half width is approximately equal to Eg by kBt to the power 1/6 into just kBt. Now it is important to note the energy dependence. You see, the energy dependence of the fusion rate here, it resembles, so this energy dependence, it resembles the form. Which form? This form, e to the power minus x average whole square divided by twice sigma square right? So you see, this is symmetric about E0, our energy distribution, and has a shape known as bell curve, or known as a bell curve, a normal distribution, or a Gaussian distribution, right? Any questions? এটা খুব এই লাস্ট পার্ট আমি শেষ করে দিচ্ছি, তারপরে আজকে ক্লাসটা শেষ করে দেব. So you see the width of fusion window, which we described previously using the 1.8 term, you can see its physical significance when, say, at E is equal to E0 plus minus delta by 2. Then what happens? At this value, the Gaussian term it becomes exponential minus 1 or 1 by E. What does this mean? This means that plus minus delta by 2 is the energy range over which the fusion probability falls by a factor 1 by E, that is 0.37 from its maximum at E0. Okay, now you see, as we have just found out, since delta by 2 is of the order of Eg to the power 1 by 6 into kBt to the power 5 by 6, so we can write the gamma window and be expressed as E0 plus minus delta by 2, or basically approximately E0 plus minus Eg by kBt to the power 1 by 6 into kBt. Okay, that's it. So please do the homeworks as I have mentioned, and then we can discuss the rest of this in the classroom. Any questions?